We've already seen a geometric series with a finite number of terms. However, all of this pales in comparison to a geometric series with an infinite number of terms. Now, this may seem completely ridiculous that we ever hope to achieve a result from a geometric series with an infinite number of terms. However, please keep in mind that a geometric series has each successive term with a common ratio being multiplied onto it. Because there's a common ratio being multiplied onto it, there is a very special interval of common ratio values for which these successive terms get smaller and smaller and smaller and smaller and smaller to hopefully enable us to achieve any sort of result. For this, we're going to have to define two words to help us out in our infinite geometric series. The first word being convergence, the second word being divergence. If things were to diverge, they just never come together, or at least they never definitively stop in one place. If things were to converge, they do come together, or at least they do stop at one result. Let us take a closer look at the sum of a geometric series. For a sum of a geometric series of n terms, with first term a and common ratio r, we normally write it as a times 1 minus r to the power n over 1 minus r. If we were to expand this right hand side, we're going to get Sn is equal to a on 1 minus r minus ar to the power n over 1 minus r. The only term in this second line which has an n in it, the number of terms, is just this second term. Let's compare different a values and different r values and plot it out on what we call a dot plot to see how a geometric series behaves. Let's take a look at the sum of a geometric series with an infinite number of terms. Let us consider firstly a geometric series whose first term is a positive number and whose common ratio value is 0. This was the expanded version of the full form of a geometric series, and this is the geometric series. Let's call this equation 1 and let's call this equation 2. From equation 1, what do we see? The sum of an infinite number of terms is going to be equal to, since a is a positive number, 1 minus 0 minus a 0 to the power infinity all over 1 minus 0. And because it's going to be 0 to the power of anything, it's going to be 0 again. A positive number times 0 is going to be 0, so we're going to be left with just S infinity is equal to a. From equation 2, what we're going to see? We're going to see that S infinity is going to be a plus a 0 plus a 0 squared plus and so on. Every successive term other than the first term is going to be 0, leaving you with just S infinity is equal to a. Although this is not the most exciting of all series, we're just saying that the sum of an infinite number of terms is just going to be one single positive number. The sum of an infinite number of terms is just one single positive number. This is still a convergent geometric series because all the infinite number of terms just stops at one single number, in this case a positive value of a. Let's carry on and see what happens if our geometric series had the first term being positive and the common ratio being 1. Let's see what happens to the first equation. Well, we're going to see that S infinity is going to be undefined because any number divided by 0 minus another number divided by 0. For equation 2, we're going to see that we got our sum to infinity is going to be a plus a plus a plus a plus a plus a. What would this look like on a dot plot? Our dot plot is simply just to see our behavior of our series as we zoom out. Now let the horizontal axis be the number of terms and the vertical axis just be the actual value of a term. However, I only said that a is a positive number. I never say what positive number it is. So let's just arbitrarily say that a is like here or something. And our first term is here, our second term is here, our third term, and so on. Since our first term is a, we get it here. Our second term is also a, we get it here. Our third term is a, we got it here, and so on. What's going to happen is that every successive term is always the same constant value of a, and if we were to add up the same positive number over and over again, eventually we're just going to get our entire sum to blow off to infinity. Let's see what will happen if we have a negative common ratio value. From the first equation, we're going to get s infinity is equal to a on 1 minus r, but the r value is positive, so it's going to be a on 1 plus 1 on a minus 1 However, we don't know the sign of minus 1 when we power it up to infinity, because infinity is not really a number, it's just the idea that the numbers go on forever. So let's just stop here and focus on the second equation. Our successive powers of minus 1 is going to make it positive a, negative a, positive a, negative a, and so on. There's always going to be some sort of a switch between the signs. What does this look like on the dot plot? Once again, because we only know that a is a positive number and there's going to be a switching between positive a, negative a, positive a, negative a, and so on and so forth, we're just going to put positive a up here, negative a down here. The first term of this infinite series is positive a. The second term of this series is negative a. The third term is positive a. The fourth term is negative a, and so on. There's always going to be some sort of an oscillation about the axis whenever we have a negative common ratio in this infinite geometric series. Let's consider an infinite series with first term being a negative number and the common ratio being half as well. Let's consider the first equation. And let's stop here. Let's not bother evaluating it, but rather let's look at the full equation. Let's factor out all the a's again. 1 half, 1/4, 1/8, and so on. How all this translate onto the dot plot? Because we know that a has got to be a negative number, let us see how this goes. A being a negative number, this is our first term. Half of that, so closer to the horizontal axis. And half of that, even closer, and even closer, and even closer, and even closer. This is still a convergent geometric series because it's going to tend towards the horizontal axis. If an infinite geometric series has the first term being a negative number, it always starts below whichever number you're going to be converging to. The formula for a sum of a geometric series to an infinite number of terms is given by a on 1 minus r. If you notice, it's just this portion of the entire formula, because at certain special values of r, this entire portion dies off. This only works if the common ratio value is between minus 1 and 1. Had it been outside of minus 1 and 1, let's say minus 1.1, or let's say 1.1 and above, or minus 1.1 and below, it doesn't work. It only works within this special interval. In summary, if the first term is positive, the entire series starts above the horizontal axis. If the first term is negative, the entire series starts below the horizontal axis. If the common ratio value is in the special interval, if the r is a positive number but still less than 1, a decay pattern forms, but the series is still convergent. If r is less than 0 but still greater than minus 1, the dot plot oscillates, but the series is still convergent. If r is greater than 1, the series is divergent, and if r is less than negative 1, the dot plots do oscillate, but it is divergent. The third term of a geometric series is 2, and the sixth term is minus 1/4. Find the sum to infinity. So the third term of a geometric series is 2, and the sixth term is minus 1/4. Writing these two terms in the a's and r's point of view, we get from T3, which we now call equation 1, T6 is called equation 2. T3 is AR squared equal to half. If we don't like it that way, we can do A is equal to 2 on R squared. Let's substitute this A into T6, and T6 is given by AR to the power of 5 equal to minus 1/4. Let's substitute this A into this A. So we get the common ratio being negative half. Going back to T3, we get A is equal to 2 on minus half squared. And so the A value is 8. Since we got the A value and the R value, we can actually find the sum of the infinite series. And the sum of the infinite series, once again, is going to be S infinity is equal to A on 1 minus R. Assuming that R is between minus 1 and 1. But because we got R is equal to minus half, that is going to be between minus 1 and 1. And so the sum of the infinite series is going to be 16 on 3.